Thank you for giving me the opportunity to speak here on low aromatic fuels and how they can mitigate contrails. Actually, I first want to acknowledge this team of co-authors. Many colleagues from DLR contributed. We had a campaign together with Deutsche Aircraft, and I will also show some results from the TUI flights. So thanks for this combined effort. I will not only concentrate on low aromatic fuels, I will also give first a short add-on on contrail avoidance, on this contrail avoidance topics from our German 100 flights trial. Then I will continue with the low aromatic fuels and their effects on contrails and on climate. I will compare that to the contrail avoidance mitigation options and then draw some conclusions at the end. And you saw this slide here. That's our global challenge, how to reduce the climate impact from contrails. You see this very nice slides of the 2019 annual mean radiative forcing from contrails calculated by Mark Stadler's team with the COLZIP model. You see the large regions with very strong radiative forcing, radiative impact from contrails above the continents and above the Northern Atlantic flight corridor. And it also, as we know, the lifetimes of contrails are very short, just a few hours, up to 10, eventual 18 hours. So there's the need to reduce the non-CO2 effects, to reduce the contrails, because that has a fast impact on climate. We also have to reduce CO2, but that stays in the atmosphere for hundreds of years. So we have to focus on both here. And I will start now with some results that we have in Germany. And I will start with the COLZIP model, where you have seen the global results, the annual mean. But the same model is also used for these contrail avoidance trials. It has been developed at DLR by Professor Schumann. And then it has been further evaluated, further developed into a pi-contrails version by Breakthrough and Imperial. So we saw the very good presentations before. Now, also at DLR, we again have re-implemented the pi-contrails version of the COLZIP model, which runs actually in two modes, the trajectory mode, in order to predict the contrails and the regions and the warming from contrails along individual trajectories, but also in this gridded mode, which is used for flight planning and in order to avoid those regions where warming contrails form. We combine that also with satellite evaluation and in order to then really find out whether contrails have formed or what could be the climate impact from those contrails, because at the end it's the satellite who tell us what is the radiative effect of those contrails that then needs to be taken into account and compared to the model results. So in Germany, we have the 100 flights program that was released by the German government, by the German ministry, and we are very happy that 4 airlines committed to make 25 flights each. So TUI Fly, Lufthansa, Condor, and DHL. Those flights have been performed last year. There's many other demonstration activities for contrail avoidance by other airlines and in other countries, but this is a German national activity supported by the German government, so that is eventually something that is new and that is also very important. And that we have the different airlines that did the job to avoid contrails. You here see the number of flights that were avoided by each airline. In addition, the airlines even committed to do some observation flights, which was not done before. With that, we can evaluate the models. And I will show you some results from the TUI flights in the next slides. Also, the contrail avoidance was planned by flight keys, for example, and also by the Lido flight system. So also the planning is very important in order to conduct these trials. So at DLR, we then did an analysis of those flights from TUI flight. We did a single flight analysis, again, comparing the planned, the optimized, and the flown flights. And we also did statistics on 17 flights that were performed within this German 100 flights trial. And you saw some numbers before. I think I can quickly go over that here now. So for those 17 flights, actually the CO2e in global warming potential for 20 or 100 years was reduced by 60 to 70%. So that's really a remarkable number. And when we compare also the flown minus the optimized flights, so the increase in flight time and the CO2 per flight, so the additional fuel flow, was in the range what was within the operational limits, so 1 to 2% more flight time. So what have we learned? In Germany, there were 108 contrail avoidance plus 61 observation flights by 4 German airlines, TUI-Fly, Lufthansa, Condor, DHL. Here I just showed a single flight evaluation for one airline and with one model, also CODESIP. We need some other models to compare to. On average, we found for those 17 flights, 60 to 70% estimated reduction in total climate impact. That's CO2 from the flights, the additional CO2 plus the CO2 equivalent from contrails. So that's a large success. And also we have 1 to 2% increase in flight time and direct CO2 emissions, which is within the range of operational costs. And you saw all these different numbers, and I think all these numbers now depend on how you compare to. Here we just compared those 17 flights where contrail avoidance were planned, but if you compare to a fleet, of course you get to different numbers that you have seen before by Alejandra, for example, and by also TUI-Fly colleagues. But at the end, all these flights show that operational contrail avoidance with a positive climate effect is kind of feasible. It's documented with these trials. Also, the additional CO2 is not a problem for climate. That's just a few or less than 1%. And also, the choice of the metric does not prevent from a start of the measures, of the activities. It will affect the climate costs, but it does not prevent from starting these activities of contrail avoidance now. And we will do 400 more flights within the EU project A for Climate. We are looking forward to this in order to even improve in future. So now I come to our in-flight measurements of aircraft emissions and contrails, where we have quite a large expertise. Since the 1994 with the sulfur campaigns, we had some concert campaigns, working together also with NADA on sustainable aviation fuels and the effects on contrails and on climate, and recently also with Airbus and Boeing on lean burn emissions and their effects on contrails. And I will show some results from the ECLIF 1 and 2 and 3 missions right now, and that is addressing now what is the effect of sustainable aviation fuels, so low aromatic fuels, on particle emissions and on contrails. And you see here on the lower axis the soot particle numbers per kilogram of fuel burned, and on the y-axis the contrail ice crystal numbers that form. And here we have measurements from different campaigns. The black symbols and the gray symbols, these are Jet A1 fuels, and the colored symbols here, these are sustainable aviation fuel blends. And here we even have 100% sustainable aviation fuel. And what you see is that with 30 to 50% sustainable aviation fuel blends, we could achieve a reduction in soot particle emissions, in ice crystals and contrails, and as the contrail climate impact scales with the ice crystal number, also the contrail climate impact is reduced. But what you also see is that the engines also have a large impact on the emitted soot particle numbers, and these are newer engines, so these are Rolls-Royce Trent WB engines with whom we performed these newer measurement results. So it's both. It's not only the sustainable aviation fuel, but it's also the engine that does have an effect on particle emissions and on contrails and on climate. And the reason why these low aromatic fuels lead to lower ice crystal numbers is what we have learned from Mark Stettler before, that the aromatics are good precursors for soot particles. So the soot particles are the good precursors for the ice particles and contrails. So when we reduce the soot particle numbers, we can reduce the contrail ice crystals, and with that the climate impact from contrails. So in our new campaign, we also wanted to see what is the effect of a turboprop, so a regional or a small to medium range aircraft, and what is the impact of 100% synthetic fuels, so e-fuels, on particle emission and contrails. And these regional aircraft, actually, they are very important because they are the reference for the future hydrogen fleet, which is also flying at small range or regional or even mid-range aircraft in the future. So we performed the Uplift mission, ClimArt mission, funded by the German ministry, and we, with our Falcon, chased a turboprop aircraft, a DO 328, and wanted to see how much does a turboprop engine emit at cruise. There's no reference database yet for those aircraft. And what is the effect of 100% synthetic e-fuels? Here we had to use a P2L proxy. It was not a sustainable fuel, but it was a coal to liquid fuel, because those sustainable e-fuels are not ready yet. That's yet to be performed, but it has the same composition as a P2L fuel. So, but it was available for our flights and provided by Sasol. So we did not only measure emissions at cruise, we also had our Voigt colleagues, our DLR colleagues, measuring the emissions on the ground, which is also very, very important, because on the ground you can really measure the emissions very close to the engine and up to 50 centimeter, but also up to a 30-meter distance. And you can measure the emissions at all the different thrust settings, which is also important. And then the models ask, can be scaled to the altitudes. The engines operate slightly different at altitudes, at the very different pressure and temperature levels. So it's very important to then combine the emission measurements on the ground also with the in-flight measurements. And these are some results, again, from the colleagues here that have observed a significant reduction in non-volatile particle emissions for different engine operating conditions for these 100% P2L fuels. And this is a slide. Now, our film from our aircraft measurements, those most recent ones, together with Deutsche Aircraft and Sasol. You see the DO 328 starting here. You see the pilot, they are really doing an incredible job here, getting into the plume, measuring the emissions. Here you see our Falcon, and the Falcon pilots, they communicate with the other aircraft in order to also indicate when we are in the plume, when we are out of the plume. You see also here now is a very nice sequence where the aircraft is almost thrown out of the contrail due to these vortices which form, and we got very nice results from this mission. I will show some results here now. That's a timeline of the near-field measurements. You see that we had a new record, about 16-meter distance, flying with the Falcon behind the turboprop DO 328. And you also see that the Falcon is a bit bending down. It was really at the lower limit of the aircraft in order to chase this aircraft short before stall, I would say. You see the particle emissions here when we get into the plume and out of the plume, total and non-volatile particles. We have heard about those total and non-volatile particles before. You see the enhancement in CO2 when we get in and out of the plume, and here we could really do emission measurements in these 20-meter distance with the very high CO2 levels, then in 100 and in up to 500-meter distance, which you can very nicely see in the CO2, which is kind of covered here in the log normal distribution of the particle emissions. We also had 2 contrail flights. The turboprop also gets to flight level 300, so it does produce contrails, and we could measure the effects on the contrails. So here you see how we got in and out of the contrails, and you see the size distribution that has been formed. So what are the results now? I showed you before the nice results for the previous engines. What is the effect of the turboprop and the synthetic fuel now? And you see that we are up down here. So even further reduction both in soot and ice particles and also in contrails. But this is on a linear scale. That's also to note. Here we have a linear scale. So to expand more, we now have to go to a logarithmic scale. And that is the picture you have seen before also. So here we have, again, the non-volatile particles, the ice crystal numbers, and contrails. That was the measurements we have done before. This is now with the turboprop engine, slightly lower than what we have seen before. But if we now would go in the low soot regime, that is more here, that is also important for lean burn conditions, but this is also important for future hydrogen technology. There the theory goes up here again, so that probably is those volatile particles that could be sulfate, aerosol, oils, organic materials that then get activated and form contrails. But that's not something I want to expand on here now. Our first results show that turboprop emissions and contrails have been measured with a 100% e-fuel, a P2L proxy. We still have to do it with a real P2L, a sustainable P2L. We observed a reduction in particle emissions in ground and also lower ice emission indices in the contrails. But what is now the contrail effect of those low aromatic or high hydrogen content fuels? So we have learned that the aromatics are the precursors for soot particle emissions, but they also go along with an increase in hydrogen content of the fuel. So a reduced aromatic content means an increase in hydrogen content of the fuel, and that's what you see here. So these are simulations, again with the COTIP model. What is the reference? Is 13.8% hydrogen. That's a fleet average right now. And you see that there's a reduction in soot particle emissions for an increasing hydrogen content of the fuel. Also, for this increasing hydrogen content, the potential regions where contrail can form is slightly larger, but the contrails ice crystal, as we have heard before, grow to larger sizes. They sediment out faster, so the mean contrail age decreases. The contrail optical thickness decreases. That also leads to a decrease in the contrail cirrus cover, and with that, to a decrease in the energy forcing of those contrails. And for the increase in hydrogen content, we would expect up to 50%, 60% soot particle reduction, and up to 50% reduction in the energy forcing from those contrails. And what you here see, those ranges, that would be the effects which we would expect for sulfur, a change in the sulfur content of the fuel, because the sulfur also leads to those volatile particle formation. So if the fuel sulfur content is higher, we get to this upper line here. If the fuel sulfur content is lower, we get to this lower line here. So that addresses the coinciding sulfur content effect on those fuels. And we have even compared this to our measurements to see how good is this parameterization with respect to the hydrogen content and the reductions. And these are reference fuels, Jet A1s, these are blend fuels, and here you have the 100% blends. And what you see here is that even the reference fuels, the normal Jet A1 fuels, already have a large spread, so you can gain some contrail climate reduction effect when using clean fuels, on clean Jet A1 fuels. And then, of course, it depends on the ratio, on the exact aromatic and naphthalenic content, how strong the further reduction in contrail climate impact or in soot particle emissions will then be. So it's important to really regulate the hydrogen content and not the fuel blending ratio. So what are now the effects? So that is the energy forcing from sustainable aviation fuels. What is the effect in future? And I kind of stole this also from Paul Hutchins, or this idea, who will speak later and eventually expand on that even more. So here you see the effective radiative forcing of the current fleet from 2010 to 2060. You see the effective radiative forcing from CO2 emissions increasing with an increase in air traffic, 3.6% per year. This line here shows how the CO2 would evolve if we would stop all CO2 in 2025. And you see how the CO2 is slowly decreasing due to the lifetime effect, because CO2 stays in the atmosphere for a long time. Here we have a simulation of the effective radiative forcing from CO2 and contrails, so no NOx, just CO2 and contrails. You see the COVID dip down, so during COVID there was a reduction in air traffic, and that's why the contrail effect is reduced, but not the CO2, because you simply do not see that on those time scales, and then the air traffic is increasing again. And now you could see what would be the effect of sustainable aviation fuels if you take the Refuel EU aviation scenario here, and you get the range. So here we assume that in the best case, 80% CO2 reduction, because for sustainable aviation fuels you also have the CO2 reduction, and in the worst case, 20% CO2 reduction. And for the contrails, we estimate between 20 and 40% reduction, and then we end up in this range, and that also addresses these uncertainty questions. But you also see the effects from the sustainable aviation fuels. They have to be there due to the CO2 reduction, but as the CO2 has these very long lifetimes, it really takes a long time till that gets very, very effective. While when we now have a look at the measures for contrail avoidance, and here again we took some best case scenarios here and worst case scenarios here. Here we thought contrail avoidance could start in 2025, very soon, and here in 2035, so that would be the last entrance day for contrail avoidance. And you can see that alone with reducing contrails, of course, we can reduce the climate impact, the effective radiative forcing from aviation significantly. And then, of course, we can try to add those both ranges, and that is for the preferred vision then, how to get to a more climate compatible aviation in future. But it also tells you that, of course, we still have some remnants here, so we need, in addition to sustainable aviation fuel, in addition to contrail avoidance, we need hydrogen. And I'm very happy that right now I think Airbus has announced this very nice collaboration with DLR, where we probed the emissions from a hydrogen combustion engine on a glider. So that was done by a colleague of mine, Tina Jurkat. So here you see a small hydrogen engine on a glider and a kerosene engine on the glider. And you see the kerosene engine does produce a contrail, while the hydrogen engine does produce a very, very faint contrail that has been measured with our instrumentation on an egret aircraft, and we can deliver some results in future, because at the end, for reducing CO2 from aviation, we at the end will have to go to hydrogen. And that is my end. I'm just coming from a campaign from Kiruna, and we had this very nice northern lights here, there, above our Falcon aircraft, where we tested the water vapor sensors on the current fleet, on some Lufthansa aircraft, and did some measurements with our water vapor instrumentation.
Questions? Hello. Yes?
Thanks, Christine, for this very nice talk. Rafael Valderas from Bauhaus Luftfahrt. Yesterday in the socialization beer, we were already talking about not contrail avoidance, but contrail formation or target formation to cool down the planet at some point. No? And then just as an example, like they put this silver nitrate to form clouds and then make it rain. So maybe something like some chemical, something like that. Have you ever heard of something like that? That would be quite interesting for me. Thank you.
So you are kind of expanding on these geoengineering by cooling contrails, whatever.
Yeah, exactly.
Yeah, yeah.
What would be better even than soot particles to promote the formation of contrails?
Yeah, I think we wouldn't have to spread anything else. I mean, so of course there would be more efficient ice nuclei, but I think that is not something we should do with aviation. I think we should really stay with reducing the emissions from aviation. I think we don't have to divert the aircraft during the day. I mean, the cooling contrails they are good for climate, so I think we shouldn't. We could also divert aircraft more during the day hours. So instead of flying during the night, of course, it would help to fly more aircraft starting in the morning hours. We have seen that before in order to mitigate contrails. Yeah, but I think with respect to geoengineering, I think the consequences are very, very complex and probably not to be predicted. So I would stay away from that one.
We have another question here.
Thank you for a nice presentation. My name is Christiane, working with Concito. Have you done any trials with hydrotreated fossil fuels, where you have various degrees of hydrotreatment to heighten the hydrogen content?
Yeah. So we have done a modeling study on this. There's a Quanti et al. Paper. I can also send that around in 2024. We haven't. We had in one of those flights, which I showed before, there was also a kind of synthetic fuel, but we haven't really done. With Airbus together, we also have tried some hydrotreated fuels, actually desulfurized fuels. Normally the hydrotreatment goes also with the desulfurization. And yes, for the Volcan measurements, we also tested the effects of the hydrotreated fuels on contrails, and actually you see a similar effect. So higher hydrogen content and lower sulfur content leads to a reduction in the contrails. Mm-hmm. It's first steps, but it goes in the right direction also for the hydrotreated fossil fuels. Mm-hmm.
Other questions?
Hi, Katrin Sievert from ETH Zurich. Thank you so much. I have a question on the correlation that you showed between soot and ice crystal formation, because the graph that you showed in the rich burn environment, you see this nice linear relationship, right, between soot reduction and reduction ice crystal numbers. But when we go into the lean burn environment, yeah, you see this uptick. So I'm wondering whether there's any research going on estimating, looking into that relationship in the lean burn environment, or tests happening. Yeah.
Yes, it's a very important topic, this lean burn environment, where we are in this range here. So we have measurements together with Airbus, but also together with Airbus, with Boeing, where we measured 3 orders of magnitude soot particle reduction in this lean burn regime, but we also measured high contrail ice crystal numbers. So that really puts forward to that volatile particles are activated here. And that again puts forward to the need to have a look on the fuel content, because the desulfurization needs to reduce the volatile particle emissions, and with that the climate impact from the contrails also in the low soot regime. But there's lots of work ongoing also in the A4Climate project. We are investigating this low soot regime. Currently, there's about 6 to 7% of all aircraft are flying with these lean burn engines. But it's also important for future hydrogen technologies to assess what happens if the contrail formation does not occur on the soot particles. What takes over here in order to form contrails, and how we can reduce contrails also in this low soot regime.
And we have one last question here from Finley.
Thank you. Finlay Asher from Aviation Worker Group, Safe Landing. Just building on the first 2 questions, we've only got so much sustainable aviation fuel at the moment, and existing kerosene, you've got some lower aromatic, some higher, just in the population of fuel supply. So are you also thinking sort of for future, thinking about maybe daytime, nighttime flights, like maybe airports should have some sort of fuel split into low aromatic and high, and you'd put the certain fuel towards certain flights, or if you're not kind of got that far in your thinking yet? Thank you.
Yeah, there's some ideas on targeted use of sustainable aviation fuels, and that also helps to reduce both the contrail climate impact and then the CO2, and you can increase the benefit from sustainable aviation fuels when putting that onto those aircraft who fly into these warming contrail regions. And there are some papers out also, Theo et al. 2023, where we investigated this, and I think the climate impact could be the benefit could be larger by a factor of 10 when attributing a small fraction of SAF to those regions where the warming contrails form, to those flights where warming contrails form. So night flights would be preferable, yes.
Thank you so much, Christiane. Give her a big applause.